Frontier PowerPoint. Has everyone looked through that one?
No.
It looks like this, the Final Frontier. If you haven't, take a look at it. I put it under, I already posted it, but I put it under today's material as well. So look through it to kind of go, okay, these are my base, these are the golden nugget conversions, okay? The SI units, all of that. It's kind of a one-stop shop for that stuff. So the conversions, some little nuggets about history, collimators, JZAC Phantom that we use in Spec QC, just the basic of it. If they ask you a question, it'll kind of just be, hey, what's a JZAC for? And then basics of EKG, kind of just reminds you of the golden nuggets. Instrumentation. This is a good one. This I did not put in today's presentation, but this is also in your math book. I might put it in next week's, but it's here, so I don't think I need to. I'm trying to think. It is probably in the 140s or 50s in your math book. So do a couple of those. This calculation's super easy, but that's just the pixel size. What else do we have? The matrix. So this kind of goes through matrix. We're going to do some matrix and pixel questions today anyway. So just kind of look through this, and I know I saw your notes. A lot of you took notes on this already too. But this is kind of the golden nugget version. Okay. So look through this if you have not. The filters, the Butterworth being the most common. And then this is kind of a good screen here, the low pass and the high pass, just getting those straight. Not going to ask you a lot of questions, but just the basics, you know, which ones are most frequently used. Butterworth is the most common. Yeah, so look through that one. Let me just pull up ours today. And then today's. All right, so here we go. All right, so some calculations today. So your brain might hurt, hopefully not too bad, okay? So let's start with camera sensitivity. Like I said, you might want to write once I get to the next slide, it'll have a quick equation to write down because we'll do an example problem. All right, so camera sensitivity. This is where we're trying to detect subtle changes from day to day or week to week in the hospital setting. So we want to actually do this sensitivity test, and there's no acceptable range, like it needs to be this, because everyone's camera will be different, and it will depend on, you know, the specific collimator thickness you use, how many PMT tubes you have. A variety of things will affect this, but the bottom line is it's something that you would look at day to day or week to week and make sure there's no increase in variations or decrease in variations, any subtle changes. Because if you can catch it there in a daily thing, then you avoid an emergency. Because when you actually visualize something on a flood that is wrong, it means it's like kind of an emergency. It's really bad if you can actually see it. But to use numbers, then we can kind of go, oh, we're kind of falling from where we were. Let's call in maintenance and get a preventative maintenance. They call it a PM, a preventative maintenance on our camera, okay? So to calculate the gamma camera sensitivity, and usually it's in CPM, and then this is supposed to be micro sensitivity as counts per minute, and micro curies per minute. The source CPM minus the background, and you would divide that by the source activity in microcuries. So take the source CPM, always subtracting out that background, and you divide by the activity. Kind of straightforward. You guys probably could get this without even the calculation. So go ahead and try number one. Calculate the sensitivity of a camera that produces 26,657 counts per minute with 152 microcurie source. See what you get. If you get that one, go ahead and move on to B, the second one I'm going to ask you. Okay? So try those two. See what you get. Kind of straightforward. Oh, I needed to give you the background. The first one, the background is 340. The first one for A, your background is 340. 340 CPMs. And then the second one should be real quick as well. Shouldn't take you guys long. You have all the information. I'll give you another minute. All right. All right, let's do it. So Rachel, what did you get for A using the background at 340?
I got 173 counts per minute.
Good. So 173 counts per minute per microcurie would be that answer. Perfect. B, Teresa, what did you get for B?
I got 427 counts per minute per microcurie.
Perfect. Something like that, 427, 428 counts per minute per microcurie. Beautiful. Great job. Now, if anyone had any problem and was like, wait, I didn't get that, I messed that up, you shouldn't have, but if you did, go to the math book and practice some more of those questions, okay? Good job. Next, we're going to do another calculation. So this one is SPECT acquisition time and counts per projection. We want to consider the time, the amount of time a patient can lay on the table, and balance that with the number of counts. We need a sufficient number of counts, but also they won't lay there forever and they won't lay still. So we're always balancing that, and as you might have to create protocols when you get it into your job, or you might adjust protocols because it's not getting a high quality image. So as we're designing the protocols and putting these in, these are the things we're looking at. How long can a patient lay still? And how many counts would we need? Now you have to remember each patient will have a various amount of count rates because of body attenuation. Some are larger patients, some are thinner patients, some have good metabolism, some have better excretion rates, depends on the test. If they've got poor kidney function, or they are, not physically active all the time, and they're often bedridden or things like that. So it'll vary patient to patient, but this is a general good idea. So there's 3 calculations associated with this. They're very easy. I don't think you're gonna have any problem with it, but you can calculate the SPECT total acquisition time. You can calculate the SPECT time per projection, and you can calculate the SPECT counts per projection. Okay, so let's go to the next slide so you can see that. So the first one you want to write down is the SPECT total acquisition time. And then here's the 2 possible calculations associated with that. So the acquisition time would be the number of projections times the time per projection, or the acquisition time could be the total counts divided by the counting rate, depending on the information given. Okay, so for a board exam. All right, in the second calculation, to calculate the spec time per projection, you would just take the total acquisition time divided by the number of projections. Now, maybe you don't need to write that down, and that's very natural and makes sense to you. You can figure that out. Very logical, right? But for now, write it down. Calculate spec counts per projection is the third one. So instead of time, we're doing counts. So counts per projection, you take the total counts divided by the number of projections. Again, these are not, something students typically struggle with. They're straightforward. Just to expose you to the actual calculation once is usually sufficient. Okay, so let's go on. We've got those three calculations, and our question is, we have a 3 million count spec study that's to be performed on a Phantom that produces a counting rate of 200,000 counts per minute. If the acquisition is to have 64 stops over 360 degrees, what will be the total time of acquisition? So go ahead and calculate that based on the calculations provided. Okay, Francesca, did you get this one?
No, I did not.
Okay, let's go on to Chris. Did you get this one? You're muted.
You guys realize that was,
Muted.
would that be 15 minutes, 3 million divided by 200,000?
You got it. Okay, so for the first one here, what will be the total time of acquisition? You're just going to take the 3 million counts and divide it by 200,000 counts per minute. Okay, and that will give you the 15 minutes. Okay, so that's right here. The total counts divided by the counting rate. That's that one for the total acquisition time. So that would be the best way to do that and quickest. All right, so let's do the next one. 180-degree spec study will be performed using 32 stops for 25 seconds each. If the estimated counting rate is 150,000 counts per minute, how many counts will be acquired in the study? How many counts will be acquired per stop? And how many minutes will be required for the acquisition? So take a minute and answer those questions based on that information. give you one more minute. All right, Lindsay, did you get this one?
I'm still kind of working on it and trying to put new batteries in my calculator at the same time.
Okay.
But the first one, would you take the 150,000 counts per minute and divide it by the 32 stops?
So, yeah, okay.
And then I got,
Yeah, you're approaching that right.
and then, so then I got the counts per minute per stop.
Right.
And then do I,
So
it seems,
there's
yeah.
two ways you can do that one. Let's
Okay.
start with the acquisition time first. So did anyone get the acquisition time part?
For the
I got it.
total study, I got 13 minutes, 13.3 minutes.
Perfect. Francesca,
Yeah.
perfect. Okay, so 13 minutes. The acquisition time, you guys multiply 32 stops times 25 seconds per stop, right?
Yes.
Equals 800 seconds or 13 minutes. Okay? And everyone got that, the ease to convert the 25 seconds to minutes, just dividing by 60 seconds per minute, you got the 0.42 minutes. The other way you can do that, is 32 stops times the 0.42 minutes. So either way, you get 13 minutes. So we got that one. All right, next, let's go to counts per projection. Counts per projection. Did you get that one, Lindsay? No? Okay.
no, sorry. No,
That's
I was
okay.
muted. I'm
That's
still
okay.
working on it.
Francesca, did you get that one?
Yeah. I got 62,343 counts per projection.
Yeah, that's perfect. Perfect. Good job. Okay, so basically for the counts per projection, you took 150,000 counts per minute times whichever way you did it, 0.42 minutes times projection, and you would get 63,000 counts per projection, right? Did everyone get that? Okay, and then the next one is total counts based on acquisition time. Okay, so you could have taken your 13 minutes that you got, so 13 minutes, and set that up equal to X over 150,000 counts per minute. Did anyone do it that way? No? And you would get like 1.9 million. So 1,950,000 counts. That would be the total counts. Or you can do the total count, and you can do the total counts based on count per projection, which would be 63,000 that Francesca got. This is probably the one she did. 63,000 counts per stop times and then set up a little ratio, X over 32 stops. And then you would get your number of counts. Francesca, is that the way you did yours? Kind of makes sense from where you went. So that would be about 2 million. So 2,016,000 counts on that one, if you did it that way. Okay? So it just depends. They'll vary a little. Remember, it doesn't really matter. We give you a couple different ways you can do it. They're estimates. It's not going to be an exact number. And on the board, if they had you do something like this, they're not going to give you two that are really, really close, because they know you can calculate it slightly different ways. Okay? So let's go back to that last one. So I just asked you for the total acquisition time. So you could do the same thing on this one. So if you want to go back and try another one, you could do this first example. You did what will be the total acquisition. You also could do like the time per stop and the counts per stop or projection. They might call it stop or projection. Okay? So go back to this one. Now that you tried out that other one, go back to this first one. And I think Chris did the 15-minute acquisition time where he took the 3 million counts divided by the 200,000 counts per minute, 15 minutes. What would be the time per projection on that one? This one. What would be the time per projection? Allie, did you get it?
It's like 0.2.
Good. Yeah, so all you'd have to do to get the time per projection, you would just take the 15 minutes that you got for your acquisition time and you divide it by the 64 stops. Is that what you did, Allie? Perfect.
Yeah.
Perfect. So she got like 0.23 minutes per stop. Okay? Which is approximately 14 seconds per stop. Okay? Good, excellent. And now on this same question, try out the counts per projection. So instead of time, they ask you for counts per projection. Counts per stop. What would that be? Brittany, did you get this one?
So it'd just be like the counts divided by stops. So I got like 46,875.
Beautiful. Yeah. So don't overthink these. Perfect job. Brittany was able to quickly go, okay, counts per projection. Just take that total counts, 3 million, and we're going to divide it by 64 stops that they gave us. It's approximately, and a lot of times on the board, they'll round. So they might give you an answer at 47,000 counts per stop. That's it. Easy peasy, right? Not bad. It's just realizing, okay, they're asking for acquisition time, or they're asking for time per projection or stop or counts. That's it. They'll give you the information to calculate that. All right, good. Let's move on to the next one. You guys did a nice job with that. So this one is obtaining desired flood or phantom fill activities. And so we use flood sources for a variety of purposes, and we need to produce specific counting rates depending on what we're doing, the system or what we're using it for. So the volume of the radionuclide is sometimes something we're trying to determine. So the volume that must be added to a phantom needs to be estimated. We need to estimate that volume to add to the phantom to achieve that specific desired counting rate. So the simplest method would be to determine the activity needed to produce the disintegrations per second. However, that would be simple. The geometry, the instrument sensitivity, attenuation, dead time, all these other factors will affect the quantity of incident radiation and the number of events that will be registered. So we use an easy alternative method for something like this. So we would measure a small activity in the phantom that we're going to use to determine the counting rate. A reasonable estimate of the total activity needed to produce the desired counting rate can be made using a direct proportion. So basically, we're just going to use a small activity, figure out the counting rate, and apply that to what we would need to do using direct proportion. Okay, so it's not too bad. All right, so here's the steps for this one. If we want to obtain desired flood or phantom fill activities, we want to, number one, place a known activity in a syringe, flood source, or phantom. We obtain the counting rate by placing the source at the same distance. This is the key for this one. At the same distance it will be used from the camera, that it will the actual flood source or phantom will be used. You want to make sure they're at the same distance. You can't get it on one distance and then you're actually performing it at a different distance. You got to compare apples to apples. Okay, so you just simply put this known activity in a syringe, flood source, phantom, whatever you're doing, get a counting rate, put it at that distance, mocking exactly what you will be doing, and then to determine the total activity needed to obtain the desired counting rate, you would just take that test sample counting rate divided by the test sample activity. So you'd use that small sample, get the counting rate, the activity, and then that would equal, you set it up to a direct proportion to the phantom counting rate divided by the phantom activity. Okay? So that's how you would do that. It's kind of, and again, a lot of these are very much just given the information, I bet you all of you would solve them. But just showing you what the kind of question might be, okay? So I've included that information up here, and then here's the question. In order to determine the activity needed to produce about 10,000 counts per minute, how many microcuries should be added to the phantom if 1.3 microcuries gives a counting rate of 620? Okay, so use that information, do that direct proportion, and see what you come up with. And again, it's probably kind of natural for you to do this one. Okay, DeMonte, this one's going to be yours. So when you're ready, go ahead.
I got 20.9.
Beautiful. Did everyone else get that? About 21 microcuries. Good, perfect. So I'm guessing DeMonte just put 620 counts per minute divided by 1.3 microcuries here. And then she put 10,000 count per minute divided by X microcuries to solve, okay? And then you would cross multiply, solve for X, and get about 21 microcuries. Beautiful, simple, easy peasy, right? No problem. You guys could get this without the example, I'm sure. There are more examples in your math book of these types of questions if you would like to try some more, okay? So let's move on. The total pixels by matrix size. All right, so let's move this down. So knowing the total number of pixels used when a particular matrix is selected will help you determine how much storage space will be set aside by the computer and how many images can be placed on a computer screen at a time. The matrices or formats most commonly used in NUCMED are the 64 by 64, 128 by 128, and 256 by 256. We do use some other configurations like a 256 by 128 for a whole body that would use 1/2 of the computer screen. So it just depends. If we're doing multiple whole body images or 4 statics, it'll just depend on the configuration. Most nuclear medicine computer screens are now high resolution using a 1024 by 1024 pixels or 2048 by 200,048 pixels to display our images. This area can be divided into multiple images. Like I just explained, we can use multiple images of a smaller matrix size. For example, in a dynamic first pass study, it's displayed as a series of images on the screen, with each image using 64 by 64 pixels. Okay, so it just depends on what we're doing. All of this is behind the scenes, and almost all the time, this is all set up for you. Okay, so don't get too worried about it, but very simply, we can calculate the total pixels used based on matrix size. Okay, so that's the first one you want to write down. So the total pixels, you just take the matrix height in pixels times the matrix width in pixels. Very logical. When you see those numbers, you naturally think just to multiply them together. Okay, and the second calculation associated with this topic is to calculate the number of images that can be displayed on a computer screen based on that matrix size. So the number of images that can be displayed, you would just take the total pixels on the display screen divided by the total pixels per frame, and that will give you that number. Okay, so go ahead and write those down. And then we're gonna move on to the next, we'll do an example, okay? All right, and I have them still included here. If you didn't get a chance to write them down, they're at the top. Let's try the first one. If a 128 by 128 matrix is selected, how many pixels will be included? Rachel, I think we're back to you, so whenever you're ready.
Um, 16,384.
Beautiful. So easy peasy. Sometimes students, they come across this question like, oh my gosh, what do you do? Rachel did it. Multiply the two numbers together. That's all they're asking for. Okay, so pixels would be 16,384, simply multiplying those two numbers together. Okay, the next one, let's do another one. How many 128 by 128 frames can be simultaneously displayed on a 256 by 256 computer screen? Try that one out. Okay, let's try Teresa.
I'm not sure if I did this right, but I think
Okay.
I got 4.
Perfect, you absolutely did it correct. So Teresa took 256 pixels times 256 pixels, right? And then she divided that by 128 by 128 pixels. And that would equal, if you figured that out, 65,536 total pixels divided by 16,384 pixels down here, and that would equal 4. So that is absolutely perfect. Nice job. It really doesn't get any harder than this. There's a couple more that we can go through quickly. It shouldn't take us long. All right, let's do C. How many pixels will be used in a 64 by 64 matrix? Francesca, this will be yours. You can answer as soon as you know that.
4,096.
Perfect. So multiplying those together, you are absolutely correct. All right, let's do Chris for the next one. How many 60 frames can be displayed on a 256 by 256? Perfect. Okay, nice job. So he got 16 frames. Make sure you star that. If you didn't get that one, that's just like the one Teresa did. Perfect. How many pixels are included in a 512 by 128 matrix, Lindsay?
Sorry, how many pixels are included in that?
Yeah, how many pixels if we have a 512 by 128 matrix?
65,536.
Beautiful. So just multiply them together. Excellent job. And then let's do this last one. Let's do F. How many 512 by 128 frames can be displayed simultaneously on a 512 by 512 display screen? Allie, this will go to you when you're ready.
4.
Good job. All right, so you can see it's not that bad, and just that multiplying that out. It's exactly just these two. It goes back to these two. Nice job. You should have gotten 4 frames just like Ellie did. Beautiful. Good job, everybody. All right, so let's move on to the next one, which is calculating memory based on matrix size and storage mode. Okay, so for most Nucmed computer systems, 1 byte is 8 bits, 1 word is 16 bits, or 2 bytes. 1 byte, 8 bits, 1 word, 16 bits, and that would also mean it's 2 bytes, okay? When data are acquired, each pixel can accumulate and display a predetermined maximum number of events. The maximum is determined by selecting byte or word mode. The maximum number of events that can be recorded in a pixel is calculated by 2 to the x minus 1, where x is the bits per unit. So per unit meaning byte or word. Okay, so the maximum events that can be recorded in a pixel is 2x minus 1. Okay, and x is the bits per unit. If byte mode is selected, then each pixel can record a maximum of 2 to the 8 minus 1. 2 to the 8 minus 1, if we're using byte mode. And that would be 255 bits. Okay, if word mode is used, a maximum of 2 to the 16 minus 1, or 65,535 events can be recorded. So it's giving you the maximums there, okay? And then, again, this information's on the top of the next one, so if you feel like you need that to look at that again, and then I'm giving you a little bit more information before we get to the problem. All right, so in byte mode, the computer sets aside 255 bits of memory for each pixel, and in word mode, it sets aside 65,535. Okay, so regardless of how much you actually use, that's what it sets aside. Okay, and data can be stored in either byte or word mode as well. Okay, so we're talking about acquisition and data storage. Both can use byte or word. Because 2 bytes equal a word, twice as many bytes are required to store the same amount of data as in word mode. Byte data stored as words will require half as many words as compared to byte mode. Now, sometimes the words here are too much for people, so getting to the next slide might actually help. But in each case, regardless, the same total number of bits are used. It's just how it's configured. You know, it can be a different configuration, okay? So here's your 3 calculations that you could possibly do related to computed memory, the memory based on matrix size and storage mode. So you can calculate the total memory used when data are acquired and stored in the same mode. So byte acquired and byte storage, or word acquired and word storage. Okay, so this is the calculation right here. Total memory required equals the height in pixels times the width in pixels, which we just did, times the number of frames. Okay, that's your first one. So write that down. The second calculation would be to calculate the total memory used when the data is acquired in word mode, but it's stored in byte mode. So basically the whole idea of this one is you simply multiply that memory requirement, which you just calculated here, by 2. Okay? So if it was acquired in word and stored in byte, you would multiply the number you got here for total memory by 2. And it's written out here. Number of bytes memory required is the height in pixel, width in pixel, times the frames, which is right up here, that calculation, and then times 2 bytes per word. Now, it's the opposite here in being this, instead of 2, is 1/2 down here at the bottom. So for calculating total memory used when data is acquired in byte and stored in word, we would simply multiply the memory requirement, which was the top one, by 1/2. Okay, so the number of words of memory required, height times pixel, width times pixel, frames, same thing, but this time 1/2 times 1/2 word per byte. This one can also be written as this. So if this one's easier for you, number of words of memory required is the pixels times frames divided by 2. Okay, so write those down. All right, let's go to the next page. And this again will be at the top, so if you didn't get it, that's what the last slide was. First question I want you to try. A 64 by 64 byte matrix is used to acquire 30 frames. How much memory will be required if the study is stored in byte mode? So the first thing you want to look at here is, are we matching our description here? So we're acquiring and storing both of them in the same mode, byte. Okay, so that's the first thing. So this is kind of the straightforward one. They're not switching anything on you. No tricks, just treats. Okay, so do A. See what you get. Brittany, when you're ready, go ahead and tell us what you got.
I got 122,880.
Beautiful. 122,880, 64 pixels times 64 pixels times 30 frames. Beautiful. Let's do B. DeMonte, B goes to you, but everyone please try it. Doesn't get any harder than these. A study is to be acquired and stored in 128 by 128 word mode. If 60 frames are required, how much memory will be used? What'd you get, DeMonte?
Uh, 983,040.
Yep, 983,040 words. Beautiful. So later on, if you want to go back to these, all you want to do is kind of do the other ones. To do the 2.5, go back through and look at how much memory would be needed if it's reversed. So acquired in one and stored in another. Try that out, okay? Good job. Excellent. All right. I saw the whole thing, dude. First you were like, whoa, and then you were like, whoa, and then you're like, whoa. Crush the turtle. Okay, if you haven't seen it, you need to see it by the end of the program. Finding Nemo. All right. Next, math and statistics. You ready? All right, let's do it. The radiation intensity from a point source of technetium is 9 MR per hour at 3 meters from the surface if the distance is changed to 9 meters. What is the new intensity? So these we're just gonna knock out. We're doing it, this is a little bit different now. gonna go to Rachel, so Rachel will tell us as soon as she's ready.
Is that B?
Okay, so good job. So that inverse square law, Rachel got B. Excellent job. All right, the next one. A technologist is sitting near a bone mineral densometer, which is a point source of X-rays. If the X-ray intensity at 1 meter from the X-ray beam is 0.2 MR per hour, to what distance from the X-ray beam should the technologist move to decrease total weekly exposure to the occupational limit of 2 MR per hour for a 40-hour work week? Oh, this one was gonna go to Teresa, but at any point I can change it out, so you all better try this one. If you can get this one, it does not get any harder than this for the boards.
C.
Would it be A?
Okay, so we
C,
got C. Okay, so this one is a little bit hard, and it does take a little bit of manipulation. The key part was the 40-hour work week in the calculation of the final answer. So if you didn't get it, star this one and go back and do it again. Again, this is as hard as it gets for the board exam. If you can get this and figure it out, you're in good shape. So come back. And I know on the fly, these are hard sometimes, and everyone's, waiting on you and all of that. So don't feel bad if you didn't get it, but start and go back and try to do that one again. Okay? Good job. All right, 10 millicuries is equal to how many becquerels? How many becquerels? Francesca, this one will be yours. So you just let us know when you are ready.
Is it C?
Okay. Nice job. Nice job. All right, 20 millicuries is equal to how many becquerels? Chris, this will be yours. You let us know when you have it.
Would that be A, 0.74 gigabecquerels?
Nice job. Excellent. So if you didn't get it that quick, I've got the how you would figure it out right there to quickly convert. Nice job. Life gets you down. What do? Just keep swimming. All right. Lindsay, this one will be yours. The dose equivalent for occupational whole body exposure is commonly limited to 50 millisieverts. How many rem is this? Millisieverts to rem.
Is it D5?
All right, nice job. D5 is correct. Beautiful. Again, start. If you didn't get it, go back to it. Review that Final Frontier PowerPoint with all the units. All right, a source is delivered to the nuclear medicine department, calibrated for 100 millicuries at 8 a.m. on Monday. If this radioactivity is injected in the patient at noon on the following Tuesday, what radioactivity will the patient receive? Go ahead and try this one, everybody. It will be Allie's when she is ready, but please, everybody do this one.
Do we need to know what
Oh.
kind of radioactivity it is?
Yeah,
A factor.
yeah, hold on. A source delivered to the nuclear calibrated thunder. Oh, let's see what it was. So C was the answer. And then, yeah. Okay, I'm gonna mark this one for a correction. I didn't give you the information of what it was. All right, I'll correct that. All right, let's go on to this one. Here we have information in there. A patient was ejected with I-131 on Monday at 10 a.m. On Tuesday at 10 a.m., the thyroid probe was placed over the thyroid and produced 100,000 counts. There's a problem with this question too. Who injected it? Very bad. Administered. On Thursday at 10 a.m., the probe showed 25,000 counts. What is the effective half-life in this patient's thyroid? Okay, those are your choices. Allie, whenever you're ready, you'll get this one.
Is it B?
Nice job. Excellent. She's absolutely correct. B. So if you didn't get that one, put a star. Come back to it. Okay? An effective half-life calculation. All right, next. A Molly tech generator is eluted Monday at 7 a.m., producing 1.8 curies of technetium in the eluate vial and 20 mLs of saline. What volume of eluate should be withdrawn from the eluate vial into a syringe in order to inject a patient with 20 millicuries of tech at 3 p.m.? And we all know technetium. This one's going to go to Brittany.
I think I did this one wrong. I'm closest to A.
Okay. Nice job. Yes. And sometimes on the board answers, they approximate, and they've approximated all along the way, so it does end up being slightly off. But again, they won't give you anything that's, not a possibility. They do look at all of that very, very closely. So nice job. All right. Just keep swimming. All right. If the HPL for some radionuclide in lead is 0.3 millimeters, what thickness of lead shielding is necessary to reduce the radiation exposure from 8 MR per hour to 1 MR per hour? Everybody try this one. And then DeMonte, when you get it, let us know.
D. I think
she meant to say was, it's D. She's laughing. All right, so yes, if you didn't get it, here it is written out how you should have done it, all of that with the half value layer, okay? So go back, star this one for the half value layer question if you didn't get it. Nice job. All right, the linear attenuation coefficient in lead for technetium gamma rays is 23. What percentage of these gamma rays will be absorbed by a lead apron that contains 0.6 millimeters of lead? Rachel, this one's going to be yours. Take your time, see if you can get it.
I don't remember how to do this.
All right, let's help her out, guys. Do you remember this one? That mu is that linear attenuation coefficient right here in the equation. The intensity, and this is mu. So that's the fraction of the beam absorbed in some thickness. The X is that thickness in there, the original thickness, and then the final thickness. So you would use this equation and plug that in, and you'll get 75%. Okay? Did anyone get this one? No? Okay, I'm going to write this one down, see if I can give you guys a couple more of these linear attenuation coefficients. Okay, they're not too bad. Just remembering this formula is probably the hardest part of that.
So you do the 23 centimeters times each, then what is it again?
The mu is the linear attenuation coefficient.
Oh, that's. No. I got that backwards.
Yeah,
Big I is.
so you get the intensity of the radiation. You have to have the original, and then you can break down this way, and you have to have the thickness, you know, how much, what's the absorber, it might not be lead that they give you, the thickness. And then the other thing to look for is the key, I think that people miss this one, is if they give you the linear attenuation coefficient in centimeters, and then they give you the absorbed 60 millimeters of 0.6 millimeters of lead, you have to make sure these units match. So that's probably a big issue if you don't have the matching units. Okay, so I'll throw out next time, I've got this one marked, I'll give you guys a couple more questions like this one, and then you'll be able to do it. And I'll probably start with one that the units match and then move into something where they don't match. Okay? So I've got that one marked. We'll do that one again. There might even be another one in here. I don't think I did another, but a patient's thyroid is counted with the thyroid probe and produces 8,000 counts. Then the patient's removed and the background is found to be 2,000 counts. The net, plus or minus the standard deviation in the net, is what? So this is just kind of remembering, hey, how do we do standard deviation? And for Brittany? Teresa, did you get this one?
Working on it.
Okay. As soon as you got it, let us
C.
know.
Is it C?
I got thrown off by standard deviation.
Okay. So you gotta subtract those background counts and then do the standard deviation, just usually just the square root. So let's go to this page. Did anyone get it? D?
No.
If you didn't get it, just make sure you go back and look. It's the 6,000 plus or minus the 100 counts. So you took the 8,000 minus the 2,000 background to get the 6,000, and then the standard deviation is just simply taking that square root, and that's how you would get plus or minus the 100. Okay? D. All right, so I'll throw in another standard deviation in our next one. Thyroid. All right, the gamma camera seems to be producing erratic results. A 57 cobalt flood source is counted 10 times, producing the following values. What is the chi-square value for these counts? These are your 10 numbers, and then you'll calculate this.